When humanity first looked up at the night sky, the stars were silent, unreachable points of light. For centuries, they were our myths, distant fires in the heavens. But today, we've touched every planet in our solar system through our machines. We've looked beyond the sun, and now we dare to ask, how do we leave our solar system? This is a journey that blends the limits of science with the boundless reach of imagination. If you could look far beyond Neptune, beyond the icy Kuiper belt, you'd find two tiny messengers still moving outward. Voyager 1 and Voyager 2, launched in 1977, are now the farthest human-made objects in existence. They've crossed the heliopause, the invisible edge where the sun's solar wind gives way to the thin, cold breath of interstellar space. They are, quite literally, the first emissaries of Earth to step into the space between the stars. On board Voyager is a message, a golden record. Engraved upon it are greetings in 55 languages, sounds of whales and laughter, the crackle of thunder, and the music of Beethoven and Chuck Berry. It's a love letter from Earth to the cosmos, a whisper of who we are, drifting endlessly through the dark. But the scale of this journey humbles us. Even moving at 38,000 miles per hour, Voyager would take over 73,000 years to reach Proxima Centauri, the closest star beyond our solar system. That's almost 3,000 generations of humans. In that time, mountains will erode, languages will vanish, and civilizations may rise and fall. Space, it turns out, isn't just empty, it's staggeringly empty. Less than 1 atom per cubic inch, colder than any winter night, darker than imagination itself. So why is it so hard to cross this gulf? The answer lies in the very fabric of reality. Einstein changed everything when he showed us that space and time are woven together, a fabric that bends with mass and motion. And within that fabric lies a harsh truth. Nothing with mass can ever reach the speed of light. As an object accelerates, its mass effectively increases, demanding more and more energy for each fraction of speed gained. To hit light speed would require infinite energy, the power of entire galaxies. And even if we could travel close to that speed, we'd face time dilation. For travelers, time slows down. A year on board might equal decades or centuries passing back home. So even if we could go, we'd never return to the same Earth. To cross interstellar distances, we need new ways to move, engines that defy the limits of what rockets can do. Project Orion, born during the Cold War, proposed something audacious, propelling a ship using nuclear explosions, literally detonating bombs behind a massive steel plate. It could reach up to 10% the speed of light, theoretically possible, politically impossible. Then came Project Daedalus, a British interplanetary society concept that used fusion reactions. It could reach another star in just a few centuries, but required thousands of tons of helium-3, mined from gas giants. More modern dreams are lighter, solar sails, vast sheets that ride on the pressure of sunlight, or laser sails, pushed by focused beams from Earth-based lasers. Breakthrough Starshot aims to send gram-sized probes to Proxima Centauri at 20% the speed of light, tiny explorers that could beam back pictures within a human lifetime. The Bussard ramjet is even more ambitious, a ship that scoops hydrogen from space and fuses it for fuel. But the universe is too empty. There isn't enough hydrogen out there for it to work. Then we reach the ideas that stretch reality itself. The Alcubierre warp drive, a concept born from general relativity, proposes bending space-time around a ship, shrinking the distance in front while expanding it behind. You wouldn't move through space. Space itself would move around you. But to do that, you'd need exotic matter with negative energy. something that might not even exist. Even if it did, the energy required could equal the mass of Jupiter. And if something went wrong, you might create a black hole instead of a warp bubble. Finally, there's antimatter propulsion, the most energy-dense fuel imaginable. When matter meets antimatter, both are annihilated in a burst of pure energy. 1 gram could power a spacecraft for days, but antimatter is almost impossible to make and even harder to store without it touching normal matter and exploding. If we can't go fast, maybe we can go long. Generation ships are one possibility. Self-contained ecosystems where entire societies live, work, and die among the stars. They'd carry the DNA of Earth, animals, plants, culture, memory, all preserved aboard a moving world. But how do you sustain meaning across centuries? Would the descendants of those travelers even want to continue the journey their ancestors began? Then there's the dream of cryogenic sleep, freezing travelers and waking them centuries later. It's a favorite of science fiction, but real biology resists it. Cells rupture when frozen. Organs fail when thawed. We can freeze embryos, not humans, not yet. And then comes the radical idea, mind uploading. What if instead of sending our bodies, we send our minds? If consciousness could be scanned and encoded as data, we could transmit ourselves at the speed of light, digital explorers made of code and memory. But that raises profound questions. Would that digital being still be you, or just a copy that thinks it's you? Is survival still survival if what survives is only information? Perhaps the future belongs not to humans at all, but to self-replicating machines, von Neumann probes, tiny robotic explorers that build copies of themselves using alien materials, spreading across the galaxy exponentially. In a few million years, they could explore every star in the Milky Way, but such power carries danger. Lose control, and you could create a swarm that consumes everything, a cosmic gray goo. Before we ask how to leave, we should ask why. Maybe it's about survival. Our sun will one day expand and consume Earth. Asteroids, pandemics, or even ourselves could end our story sooner. To endure, we must become a multistellar species. But maybe it's not just about survival. Maybe it's curiosity, the same drive that took us from caves to continents, from Earth to the moon. Every discovery we've made began with one act, looking up and wondering what's beyond. Around red dwarf stars like Proxima Centauri, life could persist for trillions of years, long after our own sun dies. To reach them would mean giving humanity a new home and a future measured in cosmic time, but such a journey would demand more than engines. It would demand wisdom, a civilization capable of patience, cooperation, and vision lasting millennia. To travel beyond the sun, we'd need not only better technology, but a better version of ourselves. Leaving the solar system isn't just a question of propulsion or physics. It's a test of imagination, of how far we can dream, and how long we can believe in that dream. Maybe it won't be us who go. Maybe it'll be our descendants, biological, digital, or something entirely new. But if even one voice, one fragment of memory, or one signal from Earth crosses the stars, then we will have already become a part of the universe's story. One day, far from home, some distant intelligence might find the golden record and hear the sounds of wind, laughter, and music. And in that moment, they'll know that once, long ago, we tried to reach the stars.